The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, I hope you all had a good spring break and refreshed. I spent 3 days in DC brainstorming. That was pretty good. If you recall, in the week before our last lecture, we were discussing the wave propagation in layered structures. And we spent time in deriving the reflectance, reflection coefficient if I have one layer. And there are 3 strategies. One, physically what happens if I have wave comes in. The first time the wave meet the interface, there's reflection, there's transmission. Go to the next interface, reflection, transmission. So there are infinite number of reflection and transmission. And of course, if there are absorption during the propagation of the wave in the layers, the intensity will be lost. Otherwise, it's say we wrote down the strategy is you can always do the plane wave propagation, and if you can write the plane wave form, you can sum up and do infinite series. So we didn't do that in class, but that's what the physics is. And what we spend time is this so-called resultant wave method. We say, okay, let's group this forward propagating, which has the same phase factor, all into one term, except now we don't have fixed relation between incoming and out, say, in the forward propagating, because you can say from the physics there, it's multiple addition, right? So we want to find the coefficients. And similarly, backward propagating, and we use the continuity of the Maxwell equation at the boundary, and we derive the expression for the reflection coefficient. So that's what we spend time on. And the third method, which is much more general, it's the transfer matrix method. And here you can say we're still distinguishing forward, backward propagating. And we're doing electric field. And transfer matrix method is writing down both incident, reflected, all grouped into what's the electric field component, what's the magnetic field component. And because at the interface, these are continuous, so it's easy for me to propagate this through many layers as long as I have the transfer matrix. Right? That transfer matrix is a phase factor. It's written. You have a general formula for each layer. And when you have many layers, it's just a multiplication of those layers. So that's actually most convenient to use, and people use it very often. And in fact, thin film deposition is so common. Anybody of you can pick up those methods and do design of multi-layer films to get desirable properties. And so that's, in fact, I tell you that I never really seriously took a EM wave class. That's where I started. I read the book, and you have to have that patience to write down all the terms and do your math through and get the appreciation for what's happening. It's an exercise. And if you take a square of this reflection coefficient, and here I'm assuming that it's real, N1, N2, N3 is real, because say clearly if it's a complex number, R12 is a Fresnel coefficient for each interface you can calculate. So even if it's complex number, you can use all the complex number operation to the square. But here, because I'm taking real, so I can actually write it just in terms of the regular square rather than complex conjugate. And you can say now what's interesting, what we want to get in is the phenomena. And in my expression for the reflectance, I have a cosine 2 phi term in both the numerator and the denominator. So you know then this reflectance will be a periodic varying function because of this cosine term. So let's use this for discussion. And you can, of course, use a single layer, and you take a dr d phi, right? This phi 2, you can say, is really d cosine theta is more like a thickness, effective thickness for the direction of propagation, and divide by lambda 0, right? So normalized to lambda 0. And this 2 phi 2 is because of the round trip, right? If you look at the physics, we have the reflection is coming, reflect back. So is a forward, backward, that's a factor of 2 in phase, right? So if I take this into 0, and you can find where the maximum minimum is, and it happens when sine 2 phi 2 equals 0. And for this, we have different solutions, whether it's maximum or minimum. So this, of course, it happens when if I substitute the phi 2 is 4 pi, because that's a factor of 2, n2 d2 cosine theta 2, lambda 0 is a vacuum, equals, say, multiple number of pi. That's when sine goes to 0. M is integer, right? But whether it's a maximum or minimum, so when m is odd number, so m equals 2l plus 1, let's say odd number. And in this case, at least when theta equals 0, you will find that reflectance is n1, n3 minus n2 square, and n1, n3 plus n2 square. So that's an interesting expression, right? It means if I have those conditions met at normal incidence here, there also other angle where you can write the maximum minimum. I'm here writing this because this expression is simple. You can see that if I have how I do anti-reflection coating, right? I have a surface, and I don't want any reflection. And in this case, I add a layer in between, n2. And you can say when n2 is the square root of n1, n3, you got a 0 reflection, right? So by using the interference phenomena, this is the periodic variation of reflectance is the interference phenomena, interference of light. You can have maximum reflection and minimum of reflection, right? And when m equals 2l, in this case, what happens is, again, at theta equals 0, you'll say your reflectance is n1 minus n3, n1 plus n3 square. What does it tell you? It tells you, even though you put the layer there, it doesn't matter. It's just like an interface between 1 and 3, right? So you use these effects to do different optical coatings. And here, of course, we're only talking about one layer. And you can coat many layers to have desirable properties. And people do that for many applications. I'll mention more as we go on. So this is just a simple example. One important characteristic we learn from this is when we consider wave, and here is a phi 2, right? If you look at reflectance, and what you have is, say, a periodic variation of reflectance. That's the interference phenomena, right? If you go to clean room, right? You deposit a layer of film very often. Some of you may go in the clean room, deposit a layer of film, and experienced person will look at the color of because the light, white light comes in is a broadband white light, and because of the interference effect, some color is reflect more, some color reflect less. And if you do a lot of this, you get the experience. You can tell from the color what's the thickness range you have, right? And of course, the same film, if you look at different angle, you see different color. And then again, that's because if you look at phi 2, it's angle dependent, right? The phase of the light is, say, when it depends on the trajectory it propagates in the material. So this is a one layer film. And then when we go multi-layer, right? It's hard to predict. When you add many, many layers, the interference phenomena becomes very complicated. And but say one special multi-layer is this quarter. Yes?
Sorry, which values of m correspond to minimum and which one to maximum?
Which value of m? So here you can say when this we have here, it is the this one is the minimum, right? And this one I think is the maximum. Okay, so when I have multi-layer of the film, one special case is the quarter wavelength. So when the period of layers is say the path length equals quarter wavelength, so what I have when I have multi-layer, you can choose layer 1, layer 2, and you're repeating layer 1, layer 2, right? And in this case, when I have 4 pi n1 d1 cosine theta 1 over lambda 0 plus 4 pi n2 d2 cosine theta 2 over lambda 0. And this is the effective layer 1 and layer 2, right? When they are effectively equals 2L pi, I have, in this case, the reflectance actually reach a maximum. So what happens is if you look at your, as a function of, you can combine these two as your effective phase, right? Let's say effective phase, or you say you can change either wavelengths of light. If you make your structure ready for different wavelengths, and what you'll say, reflectance have the almost perfect reflection region. Okay? And this is 1, this is 0. And when it's perfect reflecting, that means the light comes in 100% reflected, right? And what it means, light is not allowed in this periodic layer at this angle of incidence, right? And so in optics, this is called the stop bands. And in solid states, for electrons and photons, we call the band gap. If you recall, when we discussed three-dimensional crystals, right? The semiconductor band gap, that's when the wave functions of electrons are not allowed in this range of energy. So you can say, I mentioned before, for optics, the research direction is going from 1D to 3D. This object coatings people have developed over 100 years. You read the Yablovich paper that's only in 86. He said, OK, let's do 3D analogy to crystals so that this stop band happens in all directions so that you can pull a real band gap when you have such a crystal, no matter which direction of light you shine onto it, it's all reflected, right? So that's why I joked before, I had a colleague before was saying, this is not photonic crystal, it's a Bragg reflector. Because this quarter wavelength stack is called the Bragg reflector. And this is the Bragg condition. We talked before X-ray Bragg condition. When you have periodic structure, the wave cancels, right? So this is the corresponding Bragg condition, and this is a Bragg reflector. So it turns out, if you have such a periodic structure, no matter how small is the refractive index contrast, when I say no matter, as long as you have refractive index contrast, right? It can't be just no contrast at all, right? You can build many layers and have such a phenomenon. So normally, when sometimes when people make, say, we want high reflection, and they don't have the material that give one interface reflectance is here, right? You're limited by the refractive index contrast. So what you do is you use multi-layer Bragg reflectors and make a multi-layer structure. And there are many, many examples. People using those kind of effects. One is semiconductor laser. So some of the semiconductor lasers are actually made of gallium arsenide, aluminum arsenide, right? So one of these, normally a semiconductor laser has two configurations. One is the edge emitting. So this is a quantum well. We mentioned this configuration before. Quantum well typically very thin, right? 100 angstrom. So the light will go much wider region. So you use a total internal reflection. You put the aluminum gallium arsenide in the surrounding, which has a lower refractive index. And in that case, the light is in this region, and they propagate. They come out from the edge of the crystal. And the light needs to be amplified, so it needs to go certain distance, because the laser is amplified light emission, right? So the amplification is a positive absorption coefficient. We had before absorption coefficient, the light is decaying exponentially. And if you amplify, it's growing exponentially. But you need a certain distance to grow. So in this edge emitting laser, the distance for the light to oscillate is typically a few hundred micron. And so it has the, because what they do is after they grow the device, they will cleave it, leave a lateral interface between air and the semiconductor. So the light comes to the end, they will be reflected, and that's the reflectance, right? If the reflectance, if the refractive index of material typically is 3 to 4 gallium arsenide, right? You can go to say that reflectance is about what? If it's 3, that's 1/4 a square. It's a lot big, right? So so they need a long distance to amplify it. But people don't like this configuration because you have to cleave it, the light come from the edge. And people spend a lot of time trying to glue this so that light can come perpendicular to the surface. In that case, this is the quantum well region, and they have to make this certain thickness, half wavelength or full wavelength. Okay, so that's a cavity area. But the light only travel very short distance, right? So in this case, you need a multiple bounce. You need a high reflectivity so that the light is bounced back and forth, get amplified. And to get that high reflectivity, they will deposit this Bragg reflector on the top and bottom made of gallium arsenide and aluminum arsenide. So in that case, after, say, the reflectance at the surface can get over 99%. And the light comes, some of the light coming out perpendicular to the substrate. So this is a VCSEL, vertical cavity surface emitting laser. Right? So in fact, this is what got me interested in this multi-layer structure. When I first do research, I was worried the heat cannot get out because, in fact, those VCSEL were invented, were conceived in the 1970s. It was only until 1990s they start to be able to sell it because of the heating issue there. And when light goes through those multi-layer structure, they have to put a charge going through that structure. And this becomes very electrically resistive. And it turns out that also I started to realize that the heat also has trouble to go through those multi-layer structures. So that's I worked on it when I was doing my PhD. So that's the Bragg reflector, right? And if you use, for example, in your lab, sometimes you buy an interference filter. And interference filter is typically also made of Bragg reflectors. And sometimes a laser wavelengths, like you want to distinguish different wavelengths, they're all made of Bragg reflector. Another example, interesting example of those multi-layer, not necessarily periodic structure, is selective surface. Right? And when I say selective surface, I mean wavelength selective surface. And one example is in the solar thermal collectors. You want the surface absorb thermal radiation, but you do not want the surface radiate heat out, right? So so ideally, what do you want? Because the solar radiation is limited to about 2.4 micron. So wavelength of solar radiation is typically less than 2.4 micron. And you want this ideally absorb emissivity equals to 1 for this wavelength. But emissivity equals 0 beyond that. When you heat up an object, you think about Wien's law, right? Lambda T about 3,000. So if your object is 500 Kelvin, your wavelength is 10 micron. That's the peak wavelength. So the black body emission from the surface is here. So if you can minimize your emissivity to 0, you don't lose this much heat, right? So that's what the selective surface, ideally, I want the emissivity 1 and 0 here. And how you make it, right? You look at, say, typically, what is a surface that's a good reflector? That means its emittance is going to be low. Typically, metal is a good reflector, right? And if you take a copper, you take aluminum, they're shiny. If they're shiny, that's again you can calculate. Now, using the Fresnel formula, you get a refractive index or optical constant. You can calculate. But the emittance of metal is typically low. The problem is absorptance is also low, right? So what people do is they typically take this metal, and they will coat a few layers. And this you have to optimize. Computer code you optimize, depends on the refractive index. And one of this way they code is aluminum. They start with aluminum substrate. And they code, they change the, I think it's in nitrogen environment or oxygen environment, right? They change the oxygen pressure. So now you get the aluminum oxide, aluminum mixture. And if you change that pressure, each layer you can actually have different mixture. And that way they can do it really cheap. And the performance is pretty good. They can get the emissivity typically around 95% in this optical, the solar range, and emittance in the infrared range as low as 5% with 3 or 4 layer coating. Right? I went to those companies that do this kind of coating, and their vacuum chamber is as a football field. And they're doing this because in China, this is actually really low, widely used solar thermal in many, many households, over 100 million square meters deployed. Right? They do it really cheap. Right? So you have to look at those coatings, and of course, when you think of energy, you have to look at your cost. But what I want to tell you is now you can do it. Using that transfer matrix, it's a computer optimization. It's what material you choose that's realistic, right? And if you design, there are a lot of coating companies outside that will be happy to do it for you if you have the money. Okay. And next, so this is we have really the optical single layer and multi-layer calculation. We can do it now. And to continue the discussion, what I want is to look at the case when the angle of incidence at the first layer is larger than the critical angle of incidence, right? So in this case, at a single interface, we know there's total internal reflection, right? But all the formula we learned, for example, here, this formula is still valid. The only thing I assume here is real, but say if it's complex, you can use complex number. And with angle larger than angle of incidence, you can still use that formula. The math part is identical. So what's interesting is when the angle of incidence is larger than critical angle, what I have is a cosine theta 2. You can say cosine theta 2 is 1 minus sine theta 2 squared, right? Sine theta 2 using Snell law is 1 minus, okay, let's say sine theta 2 squared, and theta 2, sine theta 2 Snell law is sine theta 2 n2 equals n1 sine theta 1, right? So you can say in this case, I have sine theta 2 is larger than 1 above the critical angle. So when I do my cosine theta 1 minus sine theta 2 squared, I get an imaginary number. And that's what we discussed before. We have an evanescent wave on the other side. So if I have one single interface, this evanescent wave decay exponentially and doesn't carry energy to the other side. But so if I do this, what I write is n1 sine theta 1, n2 square minus 1. I put say this now becomes a real number, and you can say my cosine theta 2 is an imaginary number. If I substitute into this imaginary number into here, now you will say my reflectance is no longer 1. It could be say it could be less than 1, right? And similarly, your transmittance is no longer 0. So this is what happens, the optical tunneling. So this is the tunneling. Phenomenon. So what happens physically is I have a high index material N1, right? And you shoot the light above the critical angle. And normally, it's totally reflected. But on this side, there is exponentially decay evanescent wave. And now, if you say IB, cosine theta is I times B, you can say, of course, that depends on B times D2, right? Otherwise, that's exponential decay. It's an exponential function, and if this is really small, that reflectance is 1, right? If this exponential term really small, all this drop out, that's still 1. And when they say this one, phi 2, d2 times that b divided by lambda is not that small. It's very small actually. When it's very large, it drops to 0. But when it's very small, I can actually now have the reflectance that's less than the say it's no longer 1. So that's the tunneling. So what happens is this evanescent wave, when I bring a Lex surface close by, so this is N2. This N2 could be vacuum. For example, I put a glass, I put a vacuum, I put another layer of glass, right? And this, when I bring it close, this wave starts propagating again. It's allowable because of that angle Snell law in the third medium. The angle, if I use the Snell law, is N1 sine theta 1. N2 sine theta 2 already say is about critical angle, but the N3 sine theta 3. And in this medium, it could be propagating, right? So this is, in this case, what I'll have is R do not equal to 1, and transmittance is not equal to 0. So I have final transmission of a tunneling of this evanescent wave. So tunneling of and if you look at the distance for that to happen is when the separation or the thickness of the film is comparable to wavelengths. That's an exponential function, right? So that gives you the order of magnitude. So this tunneling phenomena is valid for all waves, right? All those interference phenomena, tunneling phenomena, Bragg reflectors. Bragg reflector in the case of electron is the superlattice. You read Ray Chu's paper. That's a superlattice for going from 3D to 1D, right? So all these are applicable for as long as you treat them as waves. It's just whether it's a scalar wave for electron and transverse wave for vector wave for EM, and acoustic wave is more complicated, right? Longitudinal and transverse. So if this is tunneling of evanescent wave for photon, there's corresponding, you can do all the analysis as we did for electron. So electron, what we had before is at one single interface, when wave comes in, you have reflection, you have transmission, right? And if the energy is less than the height, barrier height, you have total reflection, but you have an evanescent wave function on this side. And so again, if I put a very thin film, right? And so this is my structure, sandwich structure, layer 1, layer 2, layer 3, right? So electron wave launched from layer 1, and if the energy is less than the barrier height, U0, if this is the energy of electron, so in this case, I have evanescent wave that can, so but if my layer 2 is thin enough, it can come out and become propagating into the third medium. So that's the tunneling of electron. And you could use, again, the same analysis, similar analysis we do for the optical wave, and this is scalar wave, it's easier. You'll get the transmittance for electron in this case is a 4e energy U0 minus E, and 4e U0 minus E plus U0 square cinch function square d and 2m u0 minus e and h bar square. So this is the transmittance. And typically, this cinch function is an exponential function, so it grows large. So the first term can be dropped. If you do that, if you say approximate the exponential, this one will be 16 e u0 minus e over u0 square, and exponential 2 k2d. K2 is what we have in this bracket, and that's the wave vector in the second medium. Okay, so we gave the order magnitude of this before, but let's do it again. We said for optical waves, right, the tunneling happens when the thickness is comparable to wavelength. So if I do thermal radiation, my wavelengths come around 10 micron, and that thickness is 10 micron range, you start to have tunneling. But for the electron wave, this K2 is 2m u0 minus e h bar square. It's magnitude. So if we go to estimate again, so here the electron mass 9.1 10 to the minus 31. So if this u0 minus e is about 1 electron volts order of magnitude, right, is 1.6 10 to the minus 19, and h bar is 1 10 to the minus 34, so it's square 68. So this one I will get 6 and 10 to the 9th inverse angstrom. Oh no, inverse meter. So you can say, essentially, when k times d, when d is of the order of 1 angstrom 10 to the minus 10, my exponential is pretty appreciable, right? So in the case of electron tunneling, that happens in the angstrom range. In the case of photon tunneling, happens of the order of say wavelengths, optical wavelengths, say thermal wavelengths, right? Black body radiation peak at 300 is about 10 microns. So it's a very different scale. But the physics is all similar. So there are really a lot of interesting ideas using those phenomena. I told you before this Benish, when he interviewed at the IBM, right? So was asked to think about the idea to measure roughness of surface down to angstrom, right? So he did this using this idea. So this is layer 1, a probe. Layer 2 is a vacuum. Layer 3 is the surface you're going to measure, right? And you apply a bias voltage, and you scan over the surface. You measure current. You use your current as the feedback. That's a tunneling, right? So if your current, say based on the current, your feedback, you can maintain your height, not crash your tip. So of course, say they did the experiment and worked, but say they actually didn't know where the tunneling happened, because this is an atomic scale, right? If you look at the probe, they will cut the metal and cut a sharp tip or etch it. So there are a lot of paper where this tunneling really happened, and you magnify the probe. Eventually, there is one atom in the front, and that's probably where the current goes through, right? And so Benish got a Nobel Prize for this. But say none of you use atomic force microscope, right? That's also his invention. He did he did at the IBM Zurich, and he went to Stanford for sabbatical. But he was everybody was asking how to measure insulators. Right? This is a limit to the conductors. So I read one of his article. He said that one day he was sick. He was lying in his apartment, and looked on the roof, and came up with this idea of atomic force microscope. Why? Because there is always fundamentally, the thinking is, okay, you have a solid, and you have cantilever, right? And your first question, he say, is I'm going to scratch the surface or not? Right? If you use a cantilever on the surface, you're worried about that you scratch your surface, how you're going to measure atomic roughness. But he knows, so this is where the basic knowledge, the spring constant, right? So you know the vibration, you know the spring constant between atoms, and you go to look at what's the spring constant of a cantilever, what's the spring constant between atoms. And the atom spring constant is much stiffer. That means the cantilever will bend, right? The stiff one moves less. So people think of this idea. That's because they have the knowledge. You have to apply your knowledge and think about this. This isn't, possible, right? So he has this. And of course, there's deflection. So he knows how to measure deflection because he put a scanning tunneling microscope here. That cantilever itself is a conductor. So if you look at how the AFM at the beginning was the AFM, atomic force cantilever, plus a scanning tunneling tip to measure this deflection of the cantilever. It was later on people say, okay, there's a much easier way to do it, and that's by optical deflection. Because optical deflection is magnifying the small change in the height into angle. Angle times this distance is a magnifier, because that small angle, if you magnify the distance, you put a position detector, and you measure this voltage change at different positions. So that became much easier to implement. You see, you got to have your knowledge and got to be creative. Sometimes you also have to have a break, right? Okay. That's the electron tunneling, right? And the photon tunneling, you can easily think of the same. So there are people develop the different way of a photon tunneling microscope. One way is, this is a prism. You launch the light perpendicular to the surface, so there's no total internal reflection. But at this surface, there's a total internal reflection. So here, your reflected light, your wave has an evanescent wave here. And okay, now you bring a third surface. That's a vacuum, is your layer 2. You bring your third layer, which is a probe. You brought it close. That will interact with this evanescent wave and scatter them into propagating wave. So that's the ways people do. In fact, I think Professor Peter Shu in the department, he would do this to try to image, say, nanoparticle or a biological object with under, try to be the optical resolution, the wavelength limit, right? There are different ways to do it, but sometimes there are also crazy ways to think. Let me give you an idea that didn't work. I don't think it will work. And there was a big project by DARPA trying to do the tunneling energy conversion. And so basically, you heat up a surface. This is a T hot. This is a T cold, right? And they want to bring the two surfaces really close so the electron from the hot side tunnel to the cold side, and you have power generation. Right? There's a company you can search the web. There's called Cool Chips. Is still there, and they want to do cooling also. You apply current and you go tunnel electron from one side to the other. Principle-wise, it's all fine, but doing a thermal system with the two few Angstrom level separation, you're screwed most of the time, right? The contact kills you, right? And in fact, there is also, even last week, I was in a workshop with some people were mentioning our work because they want to do, this was a Stanford group, they want to do the tunneling, the thermionic emission, right? Thermionic emission is a material has a work function, and a few electron volts. So if you heat up the object, the electron will evaporate physically out of the surface, right? That's a thermionic emission, right? So the problem is that when you have two surfaces close by, and say not close by, far apart, when electrons go out, they create a potential because a charge in the vacuum has a potential. The other electron now will see that potential. It's hard to get to the other side. So that's a space charge effect. And so their theory, and this Stanford group is also doing, they say, OK, we're doing MEMS fabrication to make it smaller, so to reduce space charge effect, which is fine. But then when people say, OK, why don't you do this? So they say, oh, Gangcheng has studied. Because when you're getting really close, what happens is the tunneling of light actually increases heat transfer, which you don't want in energy conversion, right? So when you don't want to get the T hot, T cold too close below micron, that radiation tunneling start to come in and increase your heat transfer. Because this vacuum is good, but say so you have to see where is your balance point. And of course, we do a lot in the experiment. We do a lot of experiment where this is a T hot, this is a T cold, and we are starting the radiation transfer. That's when the two surface gets really close, I can have a tunneling, and that will significantly exceed the black body radiation. Okay, and so this is different. There are a lot of very funny, fancy, interesting physical phenomena happens at this scale, and also is an interesting question is asked, what you can do with it, right? If you invent this, it's a great impact. And some of those ideas don't work. But it's good to know what's the limit. OK, so what we have done, if you recall when we start chapter 5, this is actually the chapter I spent the most time so far, right? And what we want to find out is the transport between 2 points, point 1 and point 2. And if I know the transmission, tau from 1 to 2, and I know transmission from 2 to 1, right? And then I know how many, how much, how fast. I can count to say what's the energy flux, what's the momentum flux, what's the charge flux, right? You can do those type of transport calculations. And what we have done in the past few lectures is say how we calculate that transmission from one point to the other, be it the interface, be it the many layers, right? So now we can use this knowledge, put the story together, and write down the transport formula. If you recall, so far we have been doing the best in terms of the energy, for example, is the heat capacity, the energy stored per unit volume, which is the density of states times the number of, say, particle, average number of particle per state, times the energy per state, right? So that's the integrate together, get the total energy per unit volume. But now we're looking at the flux, and from one point to the other. So let's look at this. And this is the Landau Formalism. Landau formalism is actually a view of transport is relatively new. It's much later than other like Boltzmann and or say linear response theory transport. This was developed in the 60s and 70s by Landau at IBM. And so the basic idea is what we say. If I know the transmission from 1 to 2, I can count the flux, right? So let's say I want to count the heat because there are different ways you can write for different transport process. So from point 1 to point 2, if I allow the transmission from point 1 to point 2, right? And I can write per mode the energy, let's say, if that quantum state energy, and by point 1, I use subscript E1, right? And the tau 1 to 2, say if I have a wave as the energy E1 comes to point 1, how much is reaching point 2, right? And if at that quantum state, how many number of particles I have? So I have E1 and TE1. I use a T temperature, but I put a subscript E because there are some subtle points I'm going to comment. Okay? So this is just a one quantum state. I have not said what's the speed, right? It has to have the velocity because I'm considering the flux. So let's say if this is the z direction, okay? So this is a T z v z1. So you count this is per second now, energy of a quantum state, transmission from 1 to 2, how many particles in that quantum state, right? Now I just need to count how many total quantum states I have. That's what you had before. I sum up all the kx1, ky1, kz1, and the polarization, and that's where you start. Right? If you can do this, this is for energy, of course. You can do it for momentum. You can do it for charge. You can do it for entropy. You can do all transport problem. Okay? So my starting point, and now, you know, once you start writing this summation, the best way is converting into integration, right? So I can convert, I say the way of conversion, the difference, I do want to comment on difference. Here, before, when we do the heat capacity, we just energy times F sum up with the Kx, Ky, Kz, right? Sum up quantum states. But here, this one can depend on direction. Look, when we talk about single interface, that's angular dependent, right? So I don't have the angular symmetry anymore. The velocity could also be angular dependent. So I'm losing the symmetry. And I have to be careful when I convert using density of states. And so I'm going to write it out. Let's say polarization. And of course, K is Kx quantum state is 2 pi over Lx. That's the spacing. Right? So I can always convert the integration and dkx 2 pi Lx. And in fact, if I do flux, I should do per unit volume. And that will normalize out this Lx, Ly. And this is dky 2 pi Ly, dkz 2 pi Lz. So this is converting the summation points into integration points. I have vz1, tau 1 to 2, f, and e1, te1. Okay, and here you can do, so depends on kx, ky, kz, and typically this f is a function of energy, right? So you have the choice, convert everything in K integration or energy integration. You make your choice. You have the freedom, right? And I'm going to convert it into E. It doesn't mean it's always convenient using E, okay? And so I have dkx, dky, dkz. This is a Cartesian coordinate, right? In K space, not a real space. k-space Cartesian coordinate, and I do the spherical coordinate in k-space. So dkx, dky, dkz. If it's do dkx, dky, dkz is, if a spherical coordinate is k squared, that's the radius, sine theta, d theta, d phi. That's my conversion from Cartesian to spherical coordinate, right? So when you do, for example, if you translate this into a problem or interface, your wave comes in, right? That's your k. And it has a certain direction, theta phi. You can choose your theta phi coordinate yourself as long as you count that correctly, right? So this is what we're doing in the math-wise. And if I do this, before, again, if you think about what we had for specific heat, we had a spherical symmetry, so I can integrate theta and phi. But my problem is here it depends on theta phi, tau, right? I lose my symmetry, angle symmetry. So I cannot integrate out the general expression. I lost the advantage I had when I do specific heat. And when we do specific heat, we typically like to do energy integration. That's why I say here, it may not be necessarily you do energy integration is easiest. You might be doing momentum, just do kx, ky, kz. It's fine. But I'm used to, so if you recall what we had before, right? We say, okay, when I do this summation over, say the polarization, whatever function I'm going to do, this is a f, let's say that's the one that I'm interested, and I get a 4 pi k squared dk. That's when I had a spherical symmetry, right? When I integrate over theta and phi. And when I did that, I convert into this is dk is dk dE and times dE. So all this together plus this together gives me density of states dE, if you recall. Right? So if I combine this density of states, I got a 4 pi k squared dk, k squared, oh, here I should have dk. K squared dk is a density of state over 4 pi. Okay? So what I can write then, Q1 to 2 equals, I convert everything into energy integration. And phi integration is 0 to pi d phi. So if you look at this, right, this is my theta, my azimuthal plane is 2 pi, 0 to pi. And my theta integration has to be careful because what comes in is no longer, it's only 0 to 90 degree. It's not 0 to 180 degree. When I integrate the energy, local energy, it's 0 to 180 degree. But I'm looking at only counting what comes toward the surface, 0 to 90 degree. So it's 0 pi over 2. Okay, d theta. And say dk, I become a dE. And what's left in the bracket is Vz1, tau 1 to 2, and f E1, Te1, and times the density of states at E1. Right? So this is a dE1. And this is the energy spectrum of at the point 1. Okay. So those are the necessary evil you have to do. when you deal with transport. It's the integration in phase space, theta phi, or k, or e, depends on your choice. Oh, here, I'm sorry, okay, because there's a 4 pi, you recall, because here, when I convert this is 4 pi, I have to divide k squared dk, I have to divide 4 pi. Okay? And one further comment, if you are true expert on this, the density of states, in fact, you can write is angle dependent. If you have an isotropic crystal in each direction, you may have different density of states per unit solid angle. Okay, so this is a 1 to 2. If you can write 1 to 2, you can write 2 to 1. Okay, Q2 to 1 is the same. I'm not going to repeat. You change all this stuff here. I'm going to write here. Okay, V is A2, tau 2 to 1, F E2, T E2, and D, and say this is at E2, 4 pi. Okay, everything, all the integration is the same. And you have the lead difference, Q1 to 2, lead difference, the lead flux, is Q1 to 2 minus Q2 to 1. Mathematically, physically, it's very, conceptually, it's very easy, right? It's just the difference between the 2 points. Okay. Now comes to this a very important point. You see, if I write down this minus this, it's a pretty complex. Each time, at least you have to do 2 times integration. 2 less the integration, right? And you may easily make mistakes. And that mistake is you may violate second law when you do so. So you have to know when you do this, you have to meet the second law requirement. The second law will tell you if you have both sides at the same temperature or you have the system at the equilibrium, right? What happens? It's left to right equals right to left. As simple as that. But it's very powerful. And if you, I actually say some papers do those kind of integration. At the end, they did it wrong because they violate this idea. And this idea is the second law, but it's called the detail balance. So principle of detail balance. So what it says at the equilibrium, and Q1, 2 should be 0. There's no lead flux, and what goes from left goes from right to left. It doesn't mean there's no transport. It's just a dynamic equilibrium, left compensates right. Right? And with that, when I rewrite the difference, I actually from 2 to 1, you say 2 to 1, 2 point is either T2, E2. I can write this Q2 to 1 at a different temperature should equal to 1 to 2 at the same temperature T2. So I will write this, okay, so Q2 to 1, this is at T2, E2, and this should equal to, according to detail balance, this should equal to Q1 to 2 at TE2 and E1, right? Basically, if I just look at this term itself, at temperature T2 from 2 to 1 should be equal to 1 to 2 when the one side is also at the same temperature. That's a detail balance. And the beauty of that is now if I write the 2 to 1, everything is the integration limit. Everything is in terms of E1, right? Follow me. Let me write down the final expression then. If I use this detail balance, I can write what I have for Q12. Now the let is E1. It's whether you choose 1 or 2 actually depends on your preference, depends on the problem. Sometimes it's easier to get the transmittance from 1 to 2 than 2 to 1. So this is E1 and 0 to pi d phi and 0 to pi over 2 d theta, and I have V Z1 and tau 1 to 2 and d E1 for pi. And what's the difference now is F TE1 E1 minus F TE2 E1 DE1. So I have conveniently using the detail balance principle to write this expression in terms of only one side, either side 1 or side 2, right? And you can see I will never violate the principle of detail balance, because when two sides are the same temperature, this is 0, automatically satisfied. And I save a lot of trouble. I don't need to do 2 integration. I only need to do 1 integration. I don't need to calculate 2 coefficients. And in fact, these 2 coefficients must be related based on my detail balance principle, right? So this is a very subtle, very important. And let's use this to understand thermal boundary resistance, right? So many of you have heard thermal boundary resistance. And that's now we understand that when I have 2 medium, right, even if they are perfect interface, even they are atomic flat, but if they are 2 different materials, or even same material with different crystallographic configuration, right, what happens is at the interface I have wave comes in, I will have reflection, I have transmission. Now that you can calculate. In principle, you can calculate, right? And so I know my tau, this is 1, this side is 2. And I can apply my expression here. And to get the heat flux is proportional to the temperature difference of the 2 sides, right? So in this case, what I have, remember if you look at this, what I'm doing, this is the photon coming towards the interface from 1 to medium 2, right? So this is the corresponding temperature of this E1. And I call this actually immediate photon. This is incoming photon. And it's a highly non-equilibrium process at the interface. Interface is always a non-equilibrium transport. There's no, it's actually hard to think. And it's not an equilibrium process. And this other side, I have E2 coming in, reflection, and transmission. So that's what happens. And based on the expression I have, and you can say here, if the temperature difference on the 2 sides are not very different, I can do a differentiation of that F. So I can write this as dF dt times TE1 minus TE2, right? Okay? And delta T over Q is defined as thermal boundary resistance. So if I have a boundary, I have reflection, I will get a resistance. And it's same for any material. If you have charge reflection, you get an electrical resistance. You have, say, photon reflection, you get thermal resistance. So, and this Q12 equals TE1 minus TE2 and R prime. And let me actually also put this is RE prime, double prime. That's a specific thermal boundary resistance. So the unit here will be meter square Kelvin per watt for this. It's a specific per unit area. So if you know the area, you divide it by that. Okay. So what? So here, based on this, you can say I can calculate the thermal boundary resistance E, and 0 to pi d phi, 0 pi over 2, and d theta v z1, and tau 1 to 2, and E1 df dt, and density of states E1 4 pi, and dE1. So in theory now, you can calculate this term. You calculate density of states. You know this. You know the band structure. You know this. This velocity I'll discuss next. Okay? So you can calculate everything. Right? And but you should ask me a problem. I'm waiting for the question to be asked. You see, there's some problem here. That is, if my transmissivity equals 1, what happens? If my transmissivity equals 1, is this 0? Resistance is not 0, right? So what's the problem? In fact, the first paper on this was written by Lido, Stanford proposal. I think it was Stanford professor. And he had a discussion of this. Let's say, he said, this is, what happens if you have an imaginary surface? Right? He said, this is not applicable. You have to do this over a mean-free path. So, but the problem really lies in how we define temperature. This is a highly long equilibrium process at the interface, right? And temperature is defined based on more equilibrium concept. And if we think about at the equilibrium, the distribution function is isotropic, right? There's no direction. And what happens at this interface, if you look at it, I say this is the incoming, this is the other side incoming. Each side you have a different spectrum, right? You know that it's this together give me the spectrum, different energy distribution, right? So what I really say, what's really the temperature at this point? The temperature at the point, if you think about the local energy density at the point, gives you the temperature. If you go back to the specific heat calculation, right, the local energy is related to local temperature. And that local energy is defined based on all directions. And when I look at this point, my energy on the left side, let's say this is my T1, this is my T2. I say it's different than TE1, TE2. That's because when I look at the point 1, right, I have those photons coming in. That has a characteristic length TE1. That's only 180 degrees on this side, right? That's incoming. The other is outgoing. That's the other 180. And let's say look at this. This is incoming. That's this side. The outgoing on this side is reflection of the surface itself. So reflection depends on reflectance and the angular dependence. It may not be symmetric at all. That's one part. The other part is my transmission here on this side. Once it's transmitted, that's again modulated by my transmission, which has angular dependence. So this is a transmission. So I add these two together, that gives me the going to other direction, that part. And then it may not be completely unsymmetric. And the local energy should be defined based on you add this part, add this part, add this part, and divide by if it's the equivalent temperature. Right? So if you do an equivalent temperature, T1 and T2, you do your redo your energy balance, you will be different because this T1 will clearly depends on not only the temperature comes in, but also the transmitted from the other side. Right? So you will have to write the relation at the end, your expression. That's in the book. I'm not going to rewrite it. You get a different thermal boundary resistance. And that one in the limit when transmission is 1 is 0. Okay? I wrote that. And people typically don't know it. So I keep tell my own group, you need to read my chapter 5. Because you have to read it carefully to understand that. Because very often people are comparing wrong things. They do an experiment, and they will compare with this theory, but what they really measure is these two, and you compare apple and orange. And you'll see sometimes they have perfect comparison. You know something's wrong, okay? But this is not just this one problem. It's actually you want to check literature, it's everywhere people discuss it. People really do this kind of research, they know it. Let me give examples. And now you can use this to understand there are many interesting phenomena. What we discuss here is thermal boundary resistance. That's where I'm really interested, so I spend time on it. But say in electron, so if you have a wire or a dot, right? People do a lot of those kind of experiment where they measure the voltage here, V1 and V2, and go through a wire. And when the wire is very small, you go to very low temperature, you got a quantized conductance. And that conductance is actually independent of material. It's a universal. And same if you do heat at a very low temperature, this is all in the book, the example problem, you get a universal heat conductance. It's independent material. Okay? And then the question is, there was a question that's often people ask, if it's ballistic, why you have resistance at all? Ballistic means go from one point to the other, why you have resistance at all? Right? And you see here is those are the ballistic quantized conductance. Right? And this really depends on the definition. And in the case of your experiment, in the case where people do this quantized conductance measurement, for example, you have a carbon nanotube, you measure the conductance. You put 2 metal electrodes, right? And so you have a nanotube, you put 2 metal electrodes, and what you measure is not this temperature or electrochemical potential. You're measuring the drain and the source. This is the average over a large area. So what does that mean is what launched into this region correspond to what you measure. What's launched is your emitted electron. If you had a chance, there is a way to measure exactly the potential here of incoming plus ballistic going from this side to the other side, right? Then this point and this point is the same potential. If you use that same potential, you get an infinite conductance. Okay, so it's really how you, because those are all non-equilibrium process, and depends on how you do your measurement, how you do your, and you interpret it. So in electrical engineering, I remember I was reading a book, there was a whole section devoted to this discussion. And in fact, you go to check, once I was looking at this paper, Professor Patrick Lee in physics department had a few papers on this, quantized conductance. Same problem, same field, say different fields. It's just really, you have to spend your time to understand it. Finally, just say another example for you to think is that when I have two black body radiation between two surfaces, right? In vacuum, T1, T2. What's the temperature of photon inside? There's no equilibrium. You have two counter-propagating photons. They don't interact. Now, if you have this black body absorber, like a disk, on one side you absorb T1, on the other side you absorb T2. So at the end, your absorber temperature will be T force equals T1 force plus T2 force average. And that temperature is uniform here, right? But when you stick a thermocouple, you measure this hot side, you measure not the photon temperature, you measure solid temperature. You stick a thermocouple on this side, you measure the solid temperature. So when you do your black body, you say my Q equals sigma T1 force power minus T2 force power, right? And correspondingly, you do your Q over delta T, that's your conductance, right? It's not infinite. However, if you are able to put this detector and measure this point and this point, it's the same temperature, you should get a conductance infinite, right? So it depends on how you define it. You have to be careful. That's my point. Okay? I'll stop here.